other thing I wanted to mention is, as I said in one of the handouts in that general information sheet, I think, or in the syllabus, I won't be following the textbooks that closely, but on the other hand, there's a rough correspondence. So as we go along, I'll be suggesting the appropriate reading that more or less parallels what we're doing in the course. So for the last lecture, I forgot to tell you that, but what's happening? Oh, I see. You want I thought the reference frame was behaving unstably. So so in the two texts, the things that you might want to read are Chapter 1, all of Chapter 1 in Wald, and also pages 55 to 60 and 66 to 68. And for Schutz, also Chapter 1, reasonably, I suppose, just kind of a review. And section 5.1 and also section 7.1. When we start on cosmology, I'll give you, of course, some readings for that too. They're ands. I mean, you mean between Wald and Schutz? Yeah, they're ands. All of these things are relevant. You know, you can select whatever you like to read out of it. Yeah. Okay. So what I want to do today is finish up some of these generalities about relativity, specifically related to the concept of general covariance, which is always a confusing thing, but at the same time, certainly a crucial aspect of the whole story. And then go on and start to do, see an example of relativity at work with what seems to me the simplest example that one can treat, which is cosmology, just an idealized cosmology. But it shows not only the dynamics of the gravitational field, but also to a certain extent its interaction with matter. So it has all the elements of relativity. But first, I wanted to say something about general covariance and make some general remarks which will become, let's say, my degree of confidence that they're exactly right will go down as the number of remarks increases. But I think that at least they're all roughly right, and they give you good orientation, on how to think about these questions. As I think I mentioned last time, it's still a question of, among people like philosophers of science and so on, it's still a matter of debate what all of these things mean. But I think there's a fairly clear consensus, especially among physicists, about how one should think about it, and that's what I'll be presenting now. So the topic is what's called general covariance, and so people over there, can you see? Okay, so that's good. And it has different levels of meaning, but I would say the root meaning is that diffeomorphisms should be regarded as what we call in physics pure gauge. So let me write that down. Of course, I haven't yet defined what is a diffeomorphism. I haven't even defined what is a manifold. And so we haven't defined, I can't expect you to know exactly what these mean, except almost everyone said they'd seen a course in this before. So if you don't know exactly what it means, then wait a little bit, and in a couple of weeks you will know exactly what it means. But given a manifold M that represents space-time, there's a set of all smooth maps of M into itself is called the diffeomorphism group. Smooth invertible maps of M into itself is called the diffeomorphism group. And a particular element of the diffeomorphism, say F, which is a map of the manifold into itself, is called a diffeomorphism. And the meaning of general covariance in the technical sense, I mean, if I try to state it more precisely, what I just said in words, is that I have this manifold M, and I have a certain number of fields and particles, physical objects, if you like, all living on M or living in M. So that will include, in particular, always the metric field on M, the gravitational field, but there may be world lines, there may be electromagnetic fields, whatever it is, that describe the physics that's going on. And now we can act on those fields with the diffeomorphism, giving a new set of fields and particles and so on, new set of objects, which I'll call gamma prime, which I'll write as F of gamma, with quotes, because this is not exactly the standard notation that's used, but the meaning should be clear. It's the result of acting on those fields with the diffeomorphism of F. And so this is not only fields on M, but it's all fields on M, all particle world lines, etc. Anything that plays a role in the physics that of the kind of system that you're thinking of. So it's all, so to speak, all dynamical variables. So what general covariance, so you can always do this, you can act on these fields with a diffeomorphism. And what general covariance says is that in some sense, in the sense of physics, these are not to be distinguished from each other. That gamma and gamma prime are the same thing. I can't say that they're literally equal because there are different sets of fields, but so I've used this symbol. That means physically equivalent. Just like, as someone mentioned last week, just like two different choices of the vector potential that describe the same gauge fields. So if we want to draw a picture, this would be my poor attempt at a picture. So here's a manifold. Actually, I've thought of it as sort of the surface of the Earth in this case, the manifold. And then we have some fields. This is the part that I can't really draw very well, but let me do something. So this strange thing is just meant to be the fields. Or maybe there's some particles, and these lines show maybe distances between them as given by the metric. And then what we're saying is that we can take the same. What will a diffeomorphism do? It'll move the points of this manifold, this surface as I've drawn it, around in an arbitrary way, but in a continuous and a smooth way. But it'll distort everything. And I was looking for colored. Oh yeah, here are the colors. And so afterwards, we'll get a different set of objects. But it'll be the same things moved around. So maybe maybe this has gone down here and so on, and the distances have changed, so it may look like this. These two may be squashed. It'll be the same number if I did it right, 5 in both cases, but their locations will have moved. Okay, so it'll look at first sight like a completely different physical situation, but according to general covariance, these represent the same physics. Okay. So that's the something. Okay. So that's the root meaning of general covariance. But this has certain consequences. If we say that these are the same, these are physically indistinguishable, then it must be the case. Notice I haven't said anything about whether these fields satisfy the equations of motion, whatever they may be. Maybe they do, maybe they don't. But it must be the case, if they're really physically equivalent, it must be that this satisfies this set gamma. These are the gamma, if you like, and these are the gamma prime here. It must be the case that gamma satisfies the equations of motion, if and only if gamma prime satisfies the equations of motion. So consistency of this viewpoint, this requires that gamma is a solution if and only if gamma prime is a solution. So in other words, acting with a diffeomorphism must take solutions into solutions. Therefore, it must leave what people say sometimes is it leaves the equations form invariant. You might hear that terminology. In fact, we're not usually concerned only with the solution. In fundamental physics, as far as we know now, all the equations of motion come from an action principle. So the way to guarantee that the solutions are always the same is that the action should be always the same. So this is a slightly stronger statement, but normally you have that this is the action functional or the action integral, that the two actions are the same. So at a mathematical level, that's a more technical consequence of diffeomorphism invariant. This is S equals the action functional. Often it's just called the action, but I've added this word functional because unfortunately there's a collision of terminology. You say that the way you produce this gamma prime from this gamma, given the diffeomorphism, is an action of the diffeomorphism group on the space M. And then there's the word action as it occurs in the action principle, as like the principle of least action. And so just to distinguish them, I'll try to usually call it the action functional. Anyway, traditionally called S. Now what has this got to do? Okay, so this is the second aspect of diffeomorphism invariance, and this is the one that gets emphasized in practice. I mean, if you want a theory to look diffeomorphism invariant, then you should check that the action is not affected by the action of a diffeomorphism. Now, many of you will have seen another term which is called, instead of diffeomorphism invariance, it's called coordinate invariance. What exactly is the relation between these two? Well, that comes, we could also call this label invariance, because coordinates, of course, serve as labels of points of the manifold. So in that sense, we can just as well call it label invariance. But in that sense, it also extends beyond a continuum. It extends to other kinds of objects which may carry labels. Here I'm thinking specifically of elements of a causal set. But in general, this is the idea. How you label things shouldn't affect the physics, is the idea of coordinate invariance. Now, what has this to do with diffeomorphism invariance? So the answer, of course, is that in essence they're the same thing, although the notion of diffeomorphism is slightly more general, because it always makes sense in any manifold, whereas not every manifold can admit a complete coordinate system. So here I meant to draw a set of coordinates. Here's our manifold again, and here's a set of coordinates on it, which I can call X. Maybe I should have used colors. So, okay. So in other words, I call them X because what this coordinate system does is it attaches to any point of the manifold a set of values of the coordinates X. Okay. Now suppose that living in this manifold, there's some fields and so on. So I'll just represent them because I couldn't draw anything more sophisticated than this, I'll just represent it by a circle, right? And I call it not gamma prime, sorry, I'll call it gamma. So these are the fields. Now, diffeomorphism invariance says what? It says that if we act on the fields by a diffeomorphism, it represents the same physical situation. So what is it to act? So there I showed an example, a sketchy, cartoon-like example of what it meant for diffeomorphism. Here we'll have the same thing. I mean, equally sketchy. So this will be turned into some other shape. Who knows what? Let's say this shape, a very wiggly shape. This will be gamma prime now. I haven't touched the coordinates. I've just acted on the physical fields and particles, which is gamma. This claim, again, is that this and this represents the same physics. It's, from a physical point of view, indistinguishable. The distinction is purely mathematical, somehow. Oops. What have I done? Now let's consider a different activity, which is another thing we could have done. Instead of acting on the fields, let me leave the fields alone, but act on the coordinates. So here I've acted with the function f, the diffeomorphism f on the fields. Now I'm going to act with f, or actually f inverse, on the coordinates. So now I haven't touched the field. It's still like this, whatever it was before. But I've deformed the coordinates, and this is harder to draw, but just to give a sense, something like this. Just some messy looking thing where I've deformed the coordinates. I've deformed them by the inverse transformation that I applied to the field. So if you think about it, it should be obvious that the relation between the coordinates and the fields and particles hasn't changed. I mean, it's changed when I go from here to here, but between here and here, it hasn't changed. It doesn't matter whether I act on the diffeomorphism and act with the diffeomorphism on the fields and leave the coordinates alone, or act on the coordinates and leave the fields alone, right? So if you're the coordinates and I'm the fields, if I transform myself in this direction, the relation between us remains the same as if I stayed still and all of you moved in that direction. So from this, now, okay, so, by the way, this is usually called, if you want to distinguish these two, this is often called an active transformation, and this is called a passive. When you act on the coordinates, it's called passive. When you act on the fields, it's called active. But now, let's ask what happens, or let's make precise what I said before. That when we have coordinates, I mean, why did we introduce them anyway? We introduced them so we could represent the field by concrete functions. So suppose, let's just look at one particular case, which is the most important one, which is the metric field, right? The metric tensor. So again, we haven't defined this yet, but we will, and I think everyone has seen it. This will look, if we're in 4 dimensions as we are, then these indices run from 0 to 3, say, then because of the symmetry, there are 10 independent functions. And so there's x mu is sort of t, x, y, z, say. Actually, I was going to think of the Schwarzschild metric. So tr, theta, phi. Anyway, 4 coordinates that are on the manifold. once we have the coordinates, we can represent the metric by these 10 functions. For example, G00, those of you who think, if you remember what the Schwarzschild metric looks like, G00, one of the 10, as a function of the spherical coordinates, is equal to minus 1 minus r naught over r, where r naught is the Schwarzschild radius. And then, for example, g theta theta is equal to r squared, and so on. So these are various functions of t, r, theta, and phi. What happens for g prime, this thing which was f of what I called f of g, acting on the this particular field by the diffeomorphism as f, it's now given by new functions, right? And the exact way it transforms, again, we'll derive later, but you've probably seen it. So if you have, I'll remind you what it looks like. It's that g prime, if we say that f of x is equal to x prime, or let's say, if I say that the point at coordinates x goes to the point whose coordinates are x prime, then g prime mu nu of x prime is given just by g alpha beta of x with these partial derivatives, right? You don't have to write this down. It's just to remind you if you already know it. Okay? So just to make things more concrete. So the effect of the diffeomorphism acting on the fields is to change, since we've not changed the coordinates, the effect of the diffeomorphism acting on the fields is to produce the same, a new set of functions to describe the same physics. However, if we do the same, if we leave the fields alone, but act on the coordinates, but with F inverse, so it produces the same, this is the same new functions. G prime mu nu. Okay. By this dot, I indicate the function g prime mu nu. So that from that point of view, there's no difference between diffeomorphism invariance and coordinate invariance. They both tell you that when you make a certain kind of transformation on the functions that represent the fields, that you haven't changed the physics. Evaluate. Well, this is a formula about the coordinate functions, but this x prime is not equal to x. Is that what you mean? I could, if you like them to be at the same coordinate values. I mean, these are now coordinate functions. I mean, these are functional representations of the metric, but so you could, if you like to see the same. I mean, whether or not this represents the same point in space-time depends on whether you're taking an active or a passive view. But if you'd like to see the same argument here, I can do it by replacing this by F inverse x prime, right? And then I could take, I don't have to call this x prime anymore. I could call it y, for example. And then maybe you've seen it more in that form. So I could change this to y and this to F inverse y. Is that what you're getting at? I'm not sure. I thought that's how you derive this. Well, so as I said, there's the active and the passive view, right? So what's called the active view is that you leave the coordinates alone and you move the fields around. The passive view, which I think maybe is the one that you have in mind, is that you leave the fields alone, but you change the coordinates so that the new coordinate values represent the same point in space-time, because now you could choose them to represent the same point in space-time. But maybe it'll be, if it's not clear, I mean, we'll discuss this when we've actually set everything up to find what is a manifold, what is a diffeomorphism, and so on. Then we'll be able to say in more detail. There was some point that I guess the only point I wanted to make is that the notion of diffeomorphism invariance itself doesn't depend on coordinates, but when you introduce a reference frame, which mathematically amounts to a coordinate system on the manifold, then diffeomorphism takes the form of coordinate invariance, with one exception, which I mentioned before, which is that it's not, that diffeomorphism is something really more general, because most manifolds don't admit a global coordinate system. So this coordinate invariance can only be regarded as a quasi-local activity. Is that clear? So, and if I ask you to name what is a manifold that doesn't admit a complete coordinate system, what might you say? A sphere, yeah. A sphere, because there's no way, there's no range of the coordinates. If I wanted to introduce 4 coordinates, x, mu, each one with its own range, whatever it may be, x0 belongs to, say, a, b, a0, b0, and so on, x mu belonging to some range, a mu, b mu. I'll inevitably define some sort of rectangular region like this, and that can never exactly be a sphere. Of course, you can get very close to being a sphere because we know you get some singularity in the coordinate system, and we know how to handle that from long experience. But strictly speaking, the sphere doesn't admit a coordinate, complete set of coordinates. But there's nothing at all lacking when it comes to the notion of a diffeomorphism of the sphere into itself. Okay. So this is general covariance as it applies specifically to general relativity. It's actually an aspect of a somewhat more general situation, and I want to say a few words on that more general situation. But before I do, is there any questions on this? Because this will come up again, but it's an absolutely key point about the physical interpretation.
Just going back to this previous question, so you said there's the one view where we're transforming the field, leaving the coordinates alone.
Right.
The other where we're transforming the coordinates, leaving the field alone. But in the first line here, you act with f on g, producing your g prime, and then you're also acting with it on the coordinates of the f of x equals x prime.
Yeah, that's a good point. I was not so happy with this formula, but so what it really meant is that f, maybe I should write it like this: f of p equals p prime, where p is so p is some point, say here, in the manifold, and then p prime is that point to which the diffeomorphism takes it. Okay. When I said that f of p equals p prime, it would have been, I mean, when I said, if I say it like this, then it's completely satisfactory. When I said that f of x equals f prime, that was a kind of misleading shorthand for the statement that x at f of p equals x prime, a new set of coordinates. Okay. So I could actually represent the coordinate system as 4 functions on the manifold. X mu maps M. Each one of them act. So that means that each point of the manifold P becomes 4 numbers, which are the X mu's. So this is a map from the manifold to R4. So if I wanted to be really more correct, I should have said it as X mu. Thinking in this way of X as a function, I should have said X of F of P is equal to X prime. What I called X prime. Okay. Is that better? Okay. Any other questions? But at this point, really all I want you to do is get the intuitive sense. I wasn't even hesitating whether to write this formula down at all. But we'll see those formulas later. And I think you've probably seen them before. But the important thing is the intuition behind it. That you can act with this diffeomorphism on anything, and so you can act with it on the physical fields, but you can also act with it on the coordinates. And it's the relative action that governs how the components of the metric change when you use this, when you carry out such an operation. So let me say something a little more. Now I want to put this in a slightly more general context, which is that a more general, this applies not just to gravity, it applies to other situations. What I'm getting at here is what I'm going to aim at is the distinction between a gauge invariance and a symmetry, as it's sometimes called. But more generally, what we have is a space which here I called sigma, but I think I'll just call it M, since it's been a manifold. It normally will be a manifold for us. A space M, what's called mathematically a space with structure. So I'm trying to describe this in a sort of abstract way that hopefully will help us see what's going on. And as I say, it applies to other things like gauge theories and so on. So we have a space with structure, and I'll name the structure sigma. So space really just means a set of points. And a structure is some mathematical objects that give shape to the space or imprint certain kind of information on it that's supposed to represent the physics. So I'll call this. So in the case of relativity, this space would be the space-time, and these structures would include everything that we needed to describe the physical world according to relativity. So it would include the topology, it would include something called the differentiable structure, it would include the metric, and so on. It could include the electromagnetic field, let's call it FAB, whatever may be there. These are the structures on the space. Then, given some set, we'll be looking at different sets of structures. In particular, we'll be dividing them into background structures and dynamical structures. But let me not do that yet. Given these structures, we have what's called the automorphism group of the structures. These are all the mappings of the space into itself that leave the structures unchanged. So it's a set of all mappings that preserve the structures, which in this case I've called sigma, or not sigma, S. That's a German S. Now, as I said, we'll divide the structures into two: the background plus the dynamical structures. So what would they be, if you remember what I was trying to say? If I look at this list here, which one, and I'm thinking of, let me ask that in a second. Let me make the other statement first. So then here is what general covariance says. This is in the more general way of looking at it. If F is an automorphism of the background and F acts on all the dynamical fields, all the dynamical structures, then what? Then it doesn't change the physics, which we often express by saying it's pure gauge. It's just in some sense giving us a different description of the same physical reality. So this is a jargon which is obviously inspired by gauge theory. Although I think historically, gauge theory was inspired by relativity. So now let's look at this in two particular cases. Maybe this will... Let's look at the case of special relativity for a second. So if we're doing special relativity, if I take this list here, some of the structures on space-time, its topology, its metric, and say the electromagnetic field, which ones would you want to put as background structures and which ones would you want to put as dynamical structures? This is background. How about the electromagnetic field? Dynamical, right? And now how about the metric? It's background. Yeah. It's fixed, right? So when we're doing special relativity, we just assume it. We don't write down equations of motion for it or anything. On the other hand, if we're doing so in this case, of the background equals technically what's called the topology and what's called the differentiable structure. Basically, it's just it's the manifold itself, whatever it takes to describe the manifold as a manifold, without giving any more information. This will describe, when we come to define what a differentiable manifold is, we'll see exactly what a differentiable structure is. But it's easier to think of what a topology is. So is the universe a sphere? Is it a sphere with antipodes identified? Is it an infinite plane topologically, and so on? And then the dynamics is basically just the rest. The dynamical fields are basically the rest. World lines of charged particles, electromagnetic fields, and so on. Now let's do the case of general relativity. See, they both fit into the same framework, but there's a subtle difference. So if we do general relativity now, again, the topology will be the background. The field, other fields, non-gravitational fields, like the electromagnetic field, will still be part of the dynamical structure. But now, I won't ask it because there's only one thing to change. Now the metric will become dynamical. That's the momentous change that happens when you go from special relativity to general relativity.
Sorry.
Yeah?
If a black hole forms, doesn't that change the topology? Not classically, no. It might quantum mechanically. But remember, when we're talking about the manifold M, we're talking about space-time itself. So that doesn't mean, even if the topology changes in the sense that in some sense at some later time you have a different topology, it's still globally just a single topology. It's still just globally a four-dimensional topology. So the only way that, as far as I know, topology cannot be yeah, that's a good question though, because you might think that that represents a dynamical topology. Like if I have a space-time that looks like this, trousers, let's say. You might say this looks like and time is running like this. You might say this looks like the topology has changed. And that's
a natural use of the words, and it has changed, but it doesn't necessarily, it has changed if we think between what it was in the past and what it is in the future. But that doesn't mean that it's a dynamical structure in itself, because as long as this is our manifold, it has whatever topology it has. The way in which it would truly become dynamical, if there was some ambiguity in the way that I'm using the words here, the way it would become dynamical in that sense would be if there was some ambiguity in what the space-time topology actually was. So, for example, there might be, and this really, as far as I know, would only arise in quantum gravity. There might be some other, topological feature. So if we were computing some sort of, say, transition amplitude from some metric here to some metric here, as you might often see it in terms of the path integral, then we have to do a sum. We would imagine doing a sum not only over all the metrics on this manifold, but also over all the metrics on this manifold. So we'd be summing over different manifolds. Then the manifold itself, that is its topology, would also become dynamical in the technical sense that I'm using it here. But so far I'm thinking of just, for the whole course, really thinking just of a classical situation. Any more? Yeah. So in the case of general relativity, what general covariance says is that the only background is the topology and the differentiable structure. Everything else is to be regarded as dynamical. Okay, so I want to make a couple of more remarks on this, and then talk about symmetries versus gauge transformations. But one other remark I wanted to make is that this one I already said. I'll just write it down again. So if F acts, this is the difference between passive and active. If F acts on the physical objects, which can include both, what I called structures before, can include both background and dynamical structure, then it's called active. If it acts, if you have a reference frame, say coordinates, if it acts on some reference frame, then it's called, and not on the physical objects, then it's passive. Another comment is that the notion of reference frame is rather different in the case of special relativity and general relativity. In the case of special relativity, it's relatively unique and rigid. So you would just, if you wanted a Cartesian reference frame, then you could easily imagine building one. At least with some idealization, you could easily imagine building one. And there's only a finite parameter set of these reference frames that you ever need to consider. So all those which are related to each other by Poincare transformations, including Lorentz transformations. However, in the case of general relativity, the notion of reference frame is much more, is much harder to realize physically, first of all. Think of designing a GPS for the Earth. It's much harder to realize physically, and it's not rigid anymore. In other words, there's no natural choice of them. There's a sort of a large infinity of different possible choices, and so they become they recede kind of into the background of the story. Sometimes people call them, I think it's a joke more than anything, instead of calling it a reference frame, which suggests some sort of rigid framework, people sometimes call it a reference, or have called it a reference mollusk, where a mollusk is, I think, something like a snail or something. So it's something that has no real clear shape to it. Another remark that I should say is that, I'll just write it down, is that this notion of general covariance, I've tried to give it a precise sense, but when you think about what its physical implications are, you find out that you can get confused. And it has whether or not it's a real condition at all. And so the people have argued that general covariance is really not a genuine physical condition, because any theory can be expressed in covariant form. In a certain sense, that's true. But what it really means is that general covariance has meaning only in an appropriate context, which is really, I suppose that's really true of almost every concept, but it's more so with general covariance. This goes back to a debate that took place between Kretschmann and Einstein, and it continues going on, about exactly what I said before: is general covariance an empty requirement or not? But in context, I would say it is. And so if we take not only general covariance as just an abstract requirement, but if we combine it with other requirements, so if we add to it some form of locality and a choice of GAB as substance, as the physical substance, or that I went back to the Takatani language, or what I've called here structure, mathematical, the relative physical structure, then it leads more or less uniquely to the Einstein equations, as we'll see. But, so it becomes powerful in context, even though just on its own, isolated, it's kind of can almost be empty. Now is another confusing point, which is the distinction. Not everyone uses this language, but I think it's pretty common. The distinction between a symmetry and a gauge invariance. So we just said that an automorphism of the background structure is pure gauge. As long as you let it act on all the dynamical structures. Which in this case, the automorphisms. By the way, is this word automorphism familiar to you? It's probably in the handout that I gave you, but is it a familiar word for most people? To whom is it not familiar? Okay, a lot of people. So this means, but how about the word isomorphism? That, I suppose that's more familiar to a lot of people. Is there someone who doesn't know the word isomorphism? No. Okay. So automorphism, so I suppose it's a contraction of self-isomorphism. So isomorphism between two mathematical objects is some mapping that takes the one into the other and preserves their form. So it's like it's like having two copies of the same thing. If you have two copies of the same thing, then you can map the one into the other, preserving all its structure. That's called an isomorphism. So you're familiar with it in the idea of groups, for example. Two groups are isomorphic. Any two cyclic groups with the same generators and so on might be isomorphic. Or you might be familiar, you are in some sense familiar with it in the case of vector spaces, like any two vector spaces of the same dimension are isomorphic as vector spaces, and so on. So automorphism is no more than the idea of isomorphism, self-isomorphism. So it's what you might call, and the word, if I weren't about to use the word to mean something slightly different, you might call it a symmetry of that object. It's a mapping of that object into itself that preserves its structure. So in the case of a manifold, this group of the isomorphisms of the manifold into itself is called the diffeomorphism group. And that's pure gauge, where by pure gauge, I just mean that it doesn't change anything about the physical reality. Now, symmetry, sometimes that's called a symmetry, but when I make this contrast in the way that people do, distinguishing a symmetry from a gauge transformation, a symmetry is a partial automorphism, or a partial automorphism. That is, it's applied to only part of the world and not the whole world. So whereas a gauge transformation doesn't change anything, a symmetry, it does change the reality. I mean, it makes a real change to the situation. So that it really does change the situation. And it seems, this is not an exact statement. Remember I said that the degree of clarity or the degree of literalness with which you can take these remarks will decrease a little bit as the remarks go on. So it's decreasing a little bit here. I'm not sure you can take this absolutely literally, but I think it's roughly true that a symmetry gives rise to a conservation law. Via what's called Noether's theorem, one of Noether's theorem, whereas the gauge transformation does not. It seems that only symmetries lead to conserved charges. However, a gauge transformation, it's not that it has no mathematical consequences, but they don't seem to be conservation laws. Instead of it has conservation, it has consequences which are identities. So an example would be what's called the contracted Bianchi identity, for those of you for whom you already know what this means. That's some identity, meaning it's true no matter what metric we put in. This is the Einstein tensor here. And this can be connected directly to diffeomorphism invariance. But it's not a conservation law. So, what's an example? What do I mean when I say? So, think of the relationship between translation invariance and momentum, which is familiar to everyone. So if we are interested in the momentum, the linear momentum of some particular subsystem, so let it be me, then it has to do, when you go through the mathematics, you can make it appear, you can bring out the fact that it has to do with translations of me with respect to the environment, that you'll be the environment. So if I translate myself, insofar as I'm not really interacting with you, as far as I'm concerned, I'm the same over here as I am over here. But as far as someone who has a bigger picture, they see that the world is different when I'm here than when I'm over here. So, and that's because my relationship to you has changed. But often, you idealize this environment. You pretend it's not there. You think, well, you're all very far away. I'm interacting very weakly. I can't even see you anymore. You're so far away. So I'll just pretend that I'm in some asymptotically flat space-time. Flatness, this emptiness goes out to infinity. Then it looks as if I haven't changed anything when I move myself over here. But in fact, I have, because I've just forgotten about the environment that's out there. So it seems to be those situations, those kind of symmetries, which can be idealized, can be derived as idealizations of acting on some subsystem with an automorphism, and not acting on the whole space-time, on the whole physical world with it, that leads to conservation laws. Maybe that'll become, may sound a little cryptic now, but hopefully it should show up when we discuss conservation laws more later. So one last comment, I think. I want to raise a question for you, but I don't want to take the time to go through it right now. But I mean, now that we've discussed sort of the historical development of general and special relativity, you might go back to this Takatani point of view that I sketched the first lecture, where we have a phenomenological stage, a kinematic, and a dynamical stage, and see whether you think it really fits. Did it work? So here at phenomenology, you would put things, for example, like the Michelson-Morley experiment. And then you could think, what is the new substance here? What are the dynamical laws, and so on. So if you think about that and have any comments on it, maybe we can take them up next time. Another comment I wanted to make is on Mach's principles. If you read many accounts of the development of relativity, you'll see that Mach's principle is featured in some of them. And in fact, I guess if you went to it was kind of ironic. If you went to the colloquium yesterday, you heard a lot about Mach's principle, and you even heard about the bucket experiment who went to the colloquium? Yeah, so you heard about the same bucket experiment that we had discussed just the day before. So what is the status of Mach's principle? In my view, or I think most people's view, in fact, it certainly had an important role in shaking up the old thinking. So it certainly played its role historically, and in fact, part of what it said is true in the sense that it's realized in general relativity, which is that matter does affect, via the Einstein equations, does affect inertia. This is this discussion we had after yesterday, 2 days ago, after the lecture. But what's wrong about it is that it denied reality to space-time. It was trying to deny reality. Well, they didn't even talk about space-time. But in modern form, it would deny the reality to space-time. It would say that inertia, as represented by, for example, the metric, does not have an independent reality and therefore doesn't affect matter. That's just wrong. In fact, when I say wrong, of course, you always can suspend judgment. Physics might change. But according to present-day physics, that's just wrong. In fact, both of them affect each other. Inertia, or more correctly, the gravitational field, has its own existence. It affects matter, and matter affects it. And the description is through the Einstein equations. So Mach's principle wanted everything to go just this way. But that's not right. What's really right is that the relation is what you might call dialectical. It's in both directions. In fact, if you want to, if you like that dialectical language, we had previously a one-way system. Before general relativity, we had inertia, or more precisely, the space-time metric. That was affecting matter, even in special relativity, but not vice versa, right? That was background. General relativity told us matter also affects inertia, but it didn't get rid of inertia. It combined them in some sort of synthesis where they both affect each other. So if you like that language of thesis, antithesis, and synthesis, then you could have, I don't know exactly what they mean, but anyway, if you took the thesis which was the pre-relativistic, that inertia affected matter, and the antithesis would be Mach's principle that matter affects inertia, and there really is, that is space, there's really no space-time there at all. General relativity is somehow the synthesis. So it seems to fit in a certain cute way. It seems to fit that idea of how things develop. And then the last comment I want to make is about, I don't have to write anything really. What was the effect? So the discussion so far was all about how general relativity developed, special relativity developed, the views it brought to our notion of space-time. But what about its effect on physics that came after it? So here I think, don't know the history completely well, but I think it's fair to say that general relativity, maybe I will write this, but I think it led, this is not the way education in physics works now. You usually learn about gauge theories before you learn about gravity, about general relativity. But in fact, I think that historically, the whole idea of a gauge theory, gauge invariance and so on, came out of general relativity. That's the original model. That I think the diffeomorphism invariance was understood first, and I'm pretty sure that the idea of gauge invariance was actually inspired by the example of gravity. So from a certain point of view, people who try to re-express gravity as quote-unquote a gauge theory are doing something unnecessary because it's already a gauge theory. It's kind of the original gauge theory. What they're trying to do is force it into a particular framework for gauge theories, which may or may not be appropriate to gravity. In my opinion, not. But in any case, that's the first remark. The second thing is that it also led to something that we're still struggling with today. It led to a conflict with quantum mechanics. Right? So the effect of general relativity, not in itself, but together with quantum mechanics, was to disrupt the unity of physics. And now we're still trying to restore that unity. That's what we call the problem of quantum gravity. And in connection with that, one of the questions that you have to face with is the metric just another field? Or does it have some status that's more fundamental or in some way different than some of the other fields? So that's all I wanted to say in this general way. So maybe I should stop and ask for some questions, if there are any at this point.
Is the progression in science always linear? Are there not feedback loops with phenomenology, and when you discover new phenomena and then you go back to the theory?
In fact, yes, indeed. So it's meant to be a circle. You could start it anywhere you like. Yes, that's right. In fact, a lot of what you might call the phenomenology of general relativity was the old dynamics. It was Newtonian gravity, right? Newtonian gravity. The first thing you have to do if you're trying to make a better theory of gravity is make sure that in some appropriate limit you recover Newtonian gravity. So that becomes part of. That's a good point. So it becomes part of the phenomenology for the next turn of the spiral.
And a naive question. Could, under extreme conditions, the dynamical variables affect the topology? For example, the so-called tear in space-time under extreme gravity. There you have the topology will change because of the dynamical variables.
What was the space-time? I didn't.
Just a naive point.
No, I just didn't hear the word that you said.
Like a tear in space-time, the topology would change under extreme gravity. So that means that the dynamical variables are affecting the topology.
Well, that was the question that came up before, I think. So, when you say that the dynamic
under extreme conditions,
like inside a black hole or something,
can the dynamical variables really change the topology itself?
Well, then that's the question. Yeah, so that's the same subtlety. What does it mean to change? Yes, I would say yes. I mean, we don't know, of course, but it seems very plausible that they could. But change in that sense doesn't make. So the answer I would give is yes. But the question came up before, does that mean that the topology becomes part of the dynamical structure, it becomes one of the dynamical structures and no longer background? And as far as we're dealing with classical gravity, that's not the case. It remains background. Even though it's changed, to say that it's changed means that at one time, what it means is that the space-time, at an early time, it looks like some 3-manifold cross R. And then at some later time, it looks like some other 3-manifold cross R. So that was this big, if it's still here. Yeah. So at an earlier time here, it looked like S1, disjoint union of S1, that is 2 circles, cross R. And at some late times, it just looks like a single circle cross R. And that would be, in the normal way of talking, a change of topology. Or in the case of a black hole, you might imagine that some little baby universe branches off from inside where classically the singularity would have been. If we were to describe this by a classical space-time, again, it would be different. At some early times, you would have just R3 for the cross R, just say flat topology. And then at late, not flat metric, but flat topology. And then at late times, you would have a more complicated topology with a branched universe and so on. So that would be change, yes. So in a certain sense, you would be right that the dynamical variables were affecting the topology. But in the technical sense that I'm using the word, it wouldn't promote the topology from background structure to dynamical structure, because we're thinking in the space-time view, not in a space developing a time view. In the space-time view, the mathematical structure that you have to work with is the topology, is the whole manifold as a whole. And that's when you write down the Einstein equations, say, or whatever the modified equations would be. They would be equations on this whole manifold. And so that would still have to be introduced as background. I mean, this is a deep question. So I do believe that when we understand quantum gravity, topology will become also a dynamical structure. But I think we have to say that as classical relativity stands now, it's not. Yeah.
I'm a bit confused now as to what constitutes a dynamical structure. Isn't, in some sense, FAB, because it's deterministic, sort of non-dynamical?
Why is it deterministic? Aren't there? We have electromagnetic waves and so on. If you say that
there's no uncertainty about what will occur, you can disregard the
yes,
value of FAB at every point in the entire manifold. There's just one structure that doesn't change.
Well, I don't know if I would say that, but there is a point to the reference to determinism, right? So if something is deterministic, in a certain sense, it never changes. But that sense means you have to know everything about it everywhere in space at one moment of time, and then you know everything in the rest of space-time. So you might say in that sense that it's not fully dynamical or something like that. It's somehow, you might feel that the change is only apparent because it's just working out something that was implicit in the initial data already. But then you would have to say that there were no dynamical structures. If that was the way you were using the word, then in classical physics, except leaving aside stochastic processes, but in classical fundamental physics, as we know it, you'd have to say there were no dynamical structures, right? Because classical physics is deterministic. So if you went back to Newtonian gravity, you'd have to say there were no dynamical structures there either. Because if you know the initial positions and momentums of everything,
Right,
then you know everything about the future. So that's not the I mean, what you're saying is in some sense a deep physical observation, but it's not. I don't think it denies the technical distinction that I'm making here.
Well,
We can have one space-time, one Minkowski space, and we can have many different electromagnetic fields on it, and they're all solutions of Maxwell's equations. This gives a huge, rich variety of, obviously, of physical possibilities. All the emails running back and forth between people and so on. Yeah.
What's the definition of gauge theory that general relativity would fit?
I tried to say so I don't want to call it a gauge theory because that suggests a particular form for the action and so on. But I mean, it's a theory which has a notion of gauge invariance in it. And that notion is the diffeomorphism group. In other words, the gauge group of general relativity is the diffeomorphism group. And when you act on all the fields and particles and so on, all the physical objects, when you act on them with a diffeomorphism, that's meant to be pure gauge. It represents the same physics, the same reality. it's actually, diffeomorphism group is a harder gauge group to deal with than the ones that you deal with in flat space gauge theories, which may be one motivation why people would like to make gravity look more like a flat space gauge theory. Is there any other? Okay, so now I want to, took a little longer than I was hoping, but let's make a start anyway on talking about cosmology. So we'll come back at some point, maybe not even this semester, but we'll come back and discuss cosmology more in detail. But here I just want to use it to illustrate how general relativity works, what it means to say that the metric is dynamical, and so on. I think that's good to do, but it's especially good to do in this course because, as you know, since you probably everyone said they did take a course in relativity before, there's an uncomfortably large amount of mathematics that you have to absorb. Basically, it's differential geometry that you have to absorb before you can really start doing relativity. So it's nice to see it at work physically before you start to go through setting up all of that mathematics. That should be enough. So let's consider a very simple, in the sense of mathematically simple, special case of relativity. Oh, here now I should give you what you can read for this. So this is for the cosmology. This is more precisely Friedman cosmology. Also called FRW, or even, I think, LFRW, various different initials. But as far as I know, it can just be called Friedman cosmology from here. And some reading might be Wald, section 5.2, and Schutz, pages 326 to 328. Some of which might be not totally comprehensible if you've not seen the relevant prerequisites. So as I said before, I think this is probably the simplest situation that illustrates matter and some dynamics with matter of gravity and the way in which it interacts with non-gravitational matter. Remember, I said last time that the word matter is kind of reserved to mean non-gravitational matter. So since now we have these nice categories, kinematics and dynamics, let's first discuss this at a kinematic level. Namely, I have to tell you what the manifold is. So the manifold, for some reason I made it curly here. Well, make it curly. So the manifold, what is the manifold in this case? As you know, probably, there are these FRW or Friedmanian type of space-times come in three varieties, depending on what space is like. So they're characterized by the fact that space is completely homogeneous and isotropic. That is, it's the same everywhere, and no matter where you are, it looks the same in every direction. So that's called the first one is called homogeneity, the same everywhere, and isotropy is the same in every direction. The only spaces that are like that, the only three manifolds that are like that are the three. Well, maybe I should ask, but probably people know it. But maybe someone can remind us. What are the three cases of the kind of space that's totally homogeneous and isotropic? Well, you give me the whole space-time, right? Yes, you give me the whole. Those are homogeneous in the stronger sense. They're homogeneous even in the space-time sense. So not only is everywhere the same, but every when is the same too. So you say Minkowski, de Sitter and anti-de Sitter. So we want to drop down one dimension. I mean, in these cosmologies, none of them will be, in general, a solution. But their spatial sections will be what will be drawn from those. So if we drop down to 3 dimensions, then what would be those? Yeah.
Besides S3, there'd also be R3. That's the Euclidean case.
Right.
And last is a hyperbolic case, I think.
Yes, exactly. You could call it maybe H3. And the only one reason I ask this is actually these are if you want global isotropy and global homogeneity, both, these are the only 3 cases. So this, however, if you're willing to look at spaces which are locally of this form, homogeneous and isotropic, then there are other topological possibilities. They're kind of interesting. This one, you can take quotients of each of these by appropriate isometry groups. And so just to give one example, there's what's called RP3, which is S3 over Z2. What does that mean? It means you take the 3-sphere and you identify points that are opposite antipodes of the sphere. That's called RP3, the projective 3-plane. And that's another possibility. And so actually there's an infinite number of groups by which you can quotient. And so the large-scale topology of space could actually be something very interesting. People have looked for that so far and not found any evidence of it, however. So I'm going to focus on this one because in some ways it's the easiest that doesn't hide any of the aspects. Of course, as probably you know, the one that best fits current observations is R3, that is space as opposed to space-time. On a large scale, as far as we can tell, it does not deviate from being flat on average. Okay, but let's take this example. So this means that now I'm drawing a space-time picture. This means this was a spatial picture, but this means that space-time looks something like this. So I'm trying to show it's cut off here, right? It couldn't go on forever unless it hits a singularity, which of course it might well do. So at every moment of time, you might ask, what do I mean by every moment of time? That would be a good question, but the claim is that there exists a slicing of this, which defines a time label, or can be defined by a time label, such that at every moment of time, the space is just a 3-sphere, right? And so at a later moment of time, again, it's a 3-sphere. So if I wanted, which I've called here sigma, so this. So now what does it take to, oh, by the way, I should say, mention that of all these ones, these 3 possibilities for homogeneity and isotropy, the only one which is compact, that is spatially closed, doesn't go off to infinity, is the 3-sphere. That makes it actually easier to talk about the action, because the action will be finite, the action function will at least finite, unless we send time to infinity too. So that's another reason for using it. So now let's try and describe this in terms of the meaningful physical variables. So we need 2 things. If we think in terms of this time slicing, I guess everyone knows what I mean by a slicing, right? Or do you? Yes? No? I just mean a partition of the space-time into 3-dimensional surfaces, which can be thought of as the space at a moment of time. So that's what we call a slice. So this is what we call a slice. And dividing up the space-time into slices is called a slicing, or in fancier language, depending on your native language. A fancier language, it's a foliation, which I guess means dividing it into leaves or something instead of, anyway. But the slices will be 3 spheres. So to characterize, to characterize a particular slice, I need to know A, which is the radius of the 3 sphere. If I give you for each possible slice, each of these topological 3 spheres, which are actually, I should say, metric 3 spheres. I mean, they're round 3 spheres. They have the geometry of a 3 sphere, not just the topology. For each one of these, I give you its radius. This is, of course, a traditional name for it, called the scale factor in cosmology. If I give you its radius, and if I also give you, so I give you only a radius. I haven't quite given you everything to know the geometry. Why? I mean, I've given you a lot of information. I'm telling you, for example, that it gets bigger, it gets smaller, like in this picture. But I haven't told you how rapidly it gets bigger and how rapidly it gets smaller. And so I need to give another bit of information. So that one is the radius. The other one is the time lapse between the 2 different slices. Okay. And so that's, thinking of them as infinitesimally close, I'll call it delta t, or dt in this case. So these 2 bits of data, given dt for every pair of slices, infinitesimally close, and giving the radius of every slice, that completely characterizes the 4 geometry. Okay, is that clear? You might ask, what do I mean by the radius, since it's not really embedded in some higher space? If that's bothering you, we can say that what I'm really giving is the circumference of the sphere, which is just defined to be 2 pi a. Okay. So the dynamical variables, so what are the non-dynamical variables? The background is just this choice of the topology of the space-time. The dynamical variables are just A and dt, d tau, sorry, tau for proper time. So this proper time represents, as you can see better if I draw it like this, it represents the orthogonal distance between the neighboring spheres. So I'm not going to derive everything now, right? I mean, this is just to give an intuitive sense of how things are. Then, since we haven't defined any of these terms technically, metric and so on, but what should be obvious, I hope, is that if I give those 2 bits of data, then I've completely defined the space-time metric. So is that pretty believable? Yes? No? Okay. So they're not only the dynamical variables, but they're the local dynamical variables, which is basically what the metric is. Now I need one more time to quit. So let me introduce another dynamical actor, which is matter. So we imagine this space-time is not empty, but filled with some sort of matter, which is called dust. Dust has a technical term in relativity. It doesn't mean something that you'd rather get rid of, but it means that something that has a form of matter that's a perfect fluid without pressure. So that's dust. So you can think of it as just a collection of independent particles not interacting with each other, and each moving along its own world line. And of course, we're thinking in a continuum language, so you have to imagine a continuous distribution of these world lines. So it's really a fluid. But if we imagine splitting it up into individual dust particles, then we can think that we can think that each particle has mass m. So it's dust particle of mass little m, which we're going to take to 0. And then there will be n of these dust particles. We're going to take n to infinity in such a way that the product, which is the total rest mass, if you like, of the dust, when you sum it up over all the particles in this spherical space, this expanding or contracting spherical space, that gives the total rest mass m. And this is not actually, in the other sense of dynamical, it's not very dynamical, right? Because the total rest mass is not changing. There's no interactions among the dust particles, and so on. So this is just one parameter, just one number that's going to describe the physical situation. So we have one overall parameter, one number, and we have two sets of local parameters, which are carrying the metric information, which is this d tau and this a. So for every slice we have an a, for every pair of slices we have a d tau, and to take into account the matter we have this number m. Oh, I should make a remark because the question came up about the sitter. So I said here that there's a unique way of choosing this foliation. The one counterexample is actually the sitter, where you can find many slices which look like a three-sphere, perfectly round three-sphere, and they're not the same slicing. I mean, there's many different slicings which represent the sitter in that way. But for all the other cases except the sitter, which is the case of pure cosmological constant and m equals 0, in all the other cases, you get a unique foliation. And in fact, the way it works is that the world lines of the dust particles are orthogonal. Well, I can just take, they're orthogonal to the hypersurfaces of constant time. In other words, because remember, orthogonal means, if you think back to special relativity, means locally at rest. What it means is that these dust particles are not moving in the cosmic rest frame. Okay, so that's set it up. So next time we'll start, I'll write down the action principle. I'll just forecast what it is. So we'll derive everything from the action. It'll be the purely gravitational action plus the action for dust. If you want to think about next time, you might amuse yourself by seeing what would you write down for the action for the dust. This one you won't be able to know unless you already know quite a lot of relativity. But the action for the dust is something you probably already know from special relativity. So we'll start there next time. Unless there's any questions right now. Yeah.
I was just trying to make sense of something you said earlier when you were contrasting symmetry with gauge invariance. You said symmetries give rise to conservation laws, whereas gauge invariance doesn't.
Right.
What about electromagnetism? Doesn't gauge invariance give rise to charge conservation?
Yes, that's an excellent example. So there's actually so if you think about it, gauge invariance is. So let me answer in two ways. If we took the case of a closed universe like we have here, what you'll find out is that there's a lot of gauge invariance still, but the total charge has to vanish. And so you don't get a useful conservation law. But that's kind of a cheat because we're not usually thinking of this closed universe. We're usually thinking, it's not a cheat, but it's not the full answer. Usually we're thinking of an isolated system, an asymptotically flat system, for example. And then indeed the total charge can be non-zero. But let's count. How many gauge invariances are there? So what is the gauge group for electromagnetism, say, in Minkowski space? It's actually an infinite dimensional group, right? So you can make an independent gauge transformation at every point. You know the rule, the formula for the gauge invariance. By the way, I guess I should let people go since it's getting late. But if you want to stick around for the rest of the discussion, please do. So you know the rule is that A mu goes to the Sabelian theory plus some grad mu of some gauge function, right? And this is a lambda of x. So there's a lambda at each point of space-time. So it's a very highly, basically, ultimately an infinite dimensional gauge group. If those gauge transformations gave rise to a conservation law, then you should have an infinite number of conservation laws, because there's actually an infinite number of generators of the group. But in fact, there's just one transformation, one conserved quantity, which is charge. Now, why is that? So you have to think of this isolated system, like I said, relative to this environment. It turns out, in a second I want to say something about Kaluza-Klein theory too, that makes it even sharper. But it turns out that the symmetry, that the gauge transformation that leads to the symmetry is one in which this lambda goes to a constant in infinity. So lambda goes to some lambda naught, as x goes to infinity. What it actually, from this point of view, how it should be thought of, is changing the phase of what's inside here relative to what's in the environment. So it is what's out there in infinity that you've wished away by pretending that nothing is out there and just dealing with no electromagnetic fields or no charged objects. They're infinity. But if there actually are charged objects out here, the symmetry that's going on, the gauge transformation, which is only partial, is changing the phase of this and leaving the phase of this unchanged. And that's the real physical change, although I'm not sure if you can see it classically. I have to think about that. But you can certainly see it quantum mechanically because, those are like in the Bohm-Maharonov effect, when you make changes in the phases, in the vector potential. So that's exactly, yeah, so that's, that's what I would say. So there's one, out of this infinitely many gauge transformations, there's one small subgroup, just an S1 subgroup, or U1, let's call it. Just a U1 subgroup that has this capability of acting on the interior without acting on the rest of the world. And that gives rise to the one conserved quantity, which is conserved charge. And that brings me to the other thing I wanted to say, which I had forgotten actually, is that there's, as you might know, there's an approach to gauge theories called Kaluza-Klein theory, which goes way back. It's not necessarily right. We still don't know, but it plays a big role in certain approaches to quantum gravity, like string theory, certainly. And it's independently a possible origin, whether or not string theory would be right or wrong, it's independently a possible origin for gauge symmetry. What happens in Kaluza-Klein, I won't say too much about it, but I just want to say that although I made the analogy before between diffeomorphism invariance and other gauge invariance, in Kaluza-Klein theory, it's not an analogy, it's an identity. What we call gauge invariance, in the narrow sense, the electromagnetic gauge invariance, becomes just a subgroup of the five-dimensional diffeomorphism group. And then in a certain sense, it may not be so clear to you what I'm saying, but this is representing this fifth dimension, which is curled into a circle. And what this symmetry does that gives rise to charge is it rotates this internal circle. And now I'm thinking that there really is a fifth dimension, so Kaluza-Klein is right, is it rotates this internal circle, but not in some, again, within this bounded region, but outside of that, it doesn't touch it. So it makes a relative rotation of those two circles. Therefore, it really is changing the physical situation. Just as I could make a translation of myself relative. So translation is a particular kind of diffeomorphism, but I just apply it to myself. Or even rotation is better, right? And it's somehow clearer. I apply it to myself, but not to the rest of the world.
So the argument is then that not all gauge transformations give rise to a conserved quantity, whereas all symmetries do.
Yeah, that's the claim. Right? As I said, I have a little doubt whether it can be taken quite literally, but I think it's essentially correct.